Hello all, let we learn today's topic BCD codes. So what is the need of your BCD codes? Basically these are termed as binary coded decimal code. In a short form we'll call this as a BCD codes. So actually these are the decimal codes. Okay, so to represent your each decimal number with the 4 binary bits, so we're going to use this binary coded decimal codes. So total we have 0 to 9 are the valid states, and then the binary combinations from 1010, which is 10 onwards, 10 to 15, so till all ones, 4 ones are not at all used in BCD. So which gives you the functional value is invalid state in a BCD. So those codes are not available in your binary coded decimal. It only codes your given decimal digits from 0 to 9 with the 4 binary bits. Now, in order to represent your given decimal number into its BCD, each decimal number is represented with the equivalent 4 binary bits. Now, for example, if I have a number which is 396, so in order to represent this 396, I require total number of bits at 12 bits, because we have 3 decimal digit here. So to represent each decimal digit, I require 4 binary bits. So 4 into 3 is total 12 bits. So to represent a k number of decimal digits, I require total number of bits in BCD is 4 into k. So now just verifying here. So now 3 equivalent in binary is 0011, 9 equivalent is 1001, 6 equivalent is 0110. As it doesn't have your 6 invalid states from 10 to 11, because it's a 10 is a 2-digit number, 15 is also 2-digit number, so which are represented with the total number of bits required to represent 10 to 15 is 8 bit. So we can't represent with the 4 bits, so in your BCD codes, hence so these are known to be the invalid states. Now so let we take an example, so of 185 to the base of 10. So this 185, which is in decimal number system, if I represent that in your BCD, the equivalent code is, so 1 is with the 4 binary bits is 001, 8 is 1000, 5 is 0101 in BCD, whereas that is equivalent to in binary is 10111001. So now, so this representation of your BCD numbers can make your communication between your machine as well as your human being. So human are more convenient to use the decimal number system, and machine is can understand the language which is in the form of your zeros and ones. So to communicate your man and machine, we are using an intermediate code called as binary codes or your BCD codes. Now, so if I am preferring the BCD, so then addition procedure we are going to calculate here. So as here the given numbers are 4 and 5, so your summation result is equivalent to 9. So then, so we no need to correct it, because 9 is a code in your BCD, so which is we have in BCD code, so there is no need of any correction. But whereas here when I'm going to the second one, so 4 plus 8 become 12. So in binary it will be equivalent to 1100. 4 plus 8 is 1100, but this 12 code is 110 is not is a invalid state in BCD. So in order to obtain that valid state, so we need to add 6, which is onto the binary summation of 12. So if I am adding that 6, so then I could get this as equivalent to the BCD equivalent, which is 1 is 001. So if I have 3 zeros, if I assume that more significant bits are 3 zeros with the 1, so then this equivalent 1 decimal is 001 and 2 is 0010. Next, third example I have taken 8 plus 9. Now here also the summation exceeds here more than 9. Then 17 is an invalid state, which is 1 0 0 0 1 is an invalid state in your BCD. Hence we are going to add your 6 number. 6 is your binary 6 is added in order to correct into your BCD equivalent. So upon adding 6, now this is also corrected to the decimal code. So 1 equivalent is 0001, 7 equivalent is 00111. So like this, so we are going to correct it if you prefer your BCD addition. Now let I take a set of number which is a decimal number of 184 plus of 576. So we need to obtain the result 760 in BCD. So if I prefer this addition, so first digit is here 1, so we represent it in BCD form with zeros, 3 zeros 1, 8 is 10000, 4 is 0100, 5 is represented with 4 bits as 0101, 7 is 0111, 6 is 0110. Now if I prefer the method of addition here, now binary rules only we need to follow. So 0 plus 0 will give you the summation result 0. 0 plus 1 is 1. 1 plus 1 is 0 with a carry of 1. So next 1 plus 0 plus 0 is equal to 1. So now verifying the first digit addition would be a invalid state because it is greater than 9. So we need to correct it by adding 6. So now upon adding 6, then we have here, so 0, 1 plus 1 is 0 and with a carry of 1, then 1 plus 0 is 1, 1 plus 1 is 0 with a carry 1, so then 1 plus 1 is 0 and the carry is forwarded to the next digit addition. So now including with the 8 plus 7, so we also have a forward carry from your previous digit addition. So when you have this, so then we are going to perform your addition bit by bit using binary rules. 1 plus 0 is 1, 1 plus 1 is 0 and here it is 1. So next 1 plus 1 is 0 with a carry 1, then 1 plus 1 is 0 with a carry 1, then 1 plus 1 is 0 with a carry 1. So now this is also, so if it is forwarding a carry upon adding your two digits, if it forwards the carry to the next digit or most significant digit, so then again we need to correct it by adding with the 6. So if your binary summation exceeds 9, correct it with addition of 6, or if a carry is forwarded from your lower significant position to the next upper significant position, there also we need to correct that with the addition of 6. So upon addition of 6, so we have here the result is 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 0 is 1. So now this 1 is forward to here. Now I am including when I am adding 1 and 5. So we have to include your forward carry from your previous addition of the digits. So now here we have 3 ones, hence the summation would generate 1 with a carry of 1. So next here 1 plus 0 is 1, 1 plus 0 is 1, so 1. So no carry. So 0 plus 1 is 1, so 0 plus 0 is 0. So now upon verifying the last digits addition, the summation is not exceeded 9 or it doesn't forwarded any carry to the next most significant position. So hence no need to correct it and you could take that as it is as a 7. So now, so this equivalent upon your correction of or your adding 6, so this equivalent becomes 7, this equivalent becomes 6 and this equivalent becomes 0. So like this we have to correct your BCD addition. So now not only you have your binary coded decimal codes, so your codes are classified into positional weighted codes and non-weighted codes. So positional weighted codes follow some positional weights like your binary number system or in your BCD. BCD only contain the 4 positional weights which are 8421. In the same manner, so there is another code which is only having positional weights of fourth position is having 2, third position is having 4, second position is having 2 and first position is having 1. So and this is your XS3 code which is also an example to the BCD code. a non-weighted code. And these non-weighted, so weighted codes can have your positional weight. Non-weighted codes doesn't have your positional weight. Using some procedure, we are going to calculate your equivalent codes from 0 to 9. So again, we have 8 4 minus 2 minus 1. So your positional weights might be a positive ones, as well as it also have your negative ones. So now we have given for each decimal digit the equivalent codes in your BCD in 2421 in XS3, as well as in 8 4 minus 2 minus 1 until 9. So we have given the codes and the unused states of your BCD. So started with 10 to 15, and here the unused states of your 2421, so which are 01012 to 1010. Unused state of your XS3s are 6 again, so which are 000 0001 0010 1101 1110 and 4 ones, and unused states of your 84 minus 2 minus 1 are given. So XS3 code is an example of non-weighted code. In this non-weighted code, you doesn't have your positional weight. So coming to this non-weighted codes, so we also have another example of non-weighted code is a gray code. So now XS3 code is obtained by adding 3 to the binary number. So this is your given or a BCD number. So now if I am adding a binary 3, so then I will obtain your, so using some procedure we said. So here the procedure is adding 3 to the given binary, then we will obtain your equivalent code. So plus 3 means, so 0011 is the decimal code of your XS3 for decimal digit of 0. Next, 1 plus 3 will be 4. So this is the code for your 1 in your XS3. Code for 2 is 3 plus 2 5. So 0101 is your code of XS3. 9 is 9 plus 3 is 12. So 1100. Like this we are going to calculate the equivalent codes in your BCD weighted and as well as your non-weighted codes. So next, another example of your non-weighted code is your gray code. So these gray codes are used for error detection, as well as these are also used to minimize your functions, and these are also used in low power design applications and to represent your analog data. So we are using this gray code. How to obtain the gray code of each digit is from 0 to 15, and this is also called cyclic code. So since here, now if I verify here from your successive code words, so there was only one bit change. So now if I compare this 0 and 001, so only one bit change is there, remaining 3 bits are having the similar logical levels. Next, 001 and 0011. So again here only one bit change, positional change, so second bit position only changed, and the remaining 3 positions are the same. So since it is having only a change in one bit only in the sequence, okay, so in the successive code word will differ by one bit position only. So next, here how to obtain the gray code is using your exclusive OR operation between your binary bits. So using that, so we would obtain your gray code. Now here the simple way is, so to obtain your gray code equivalent, so this is also an example of your reflective code. So what is a reflective code is, so now an n bit code is obtained by reflecting your n minus 1 bit. So for example, if it is a 1 bit code word, so there is a chance of only have 0 and 1. Now if I wanted to extend this, then I need to reflect by drawing a reference axis and then reflecting your the 1 bit combination on your below axis as 1 0. So like if I place a mirror on this reference axis, we have a mirror image, so which is started with a 1, and then at the end we have your 0. Next, above axis place your most significant bit, which is second bit is 0. In the below axis place your most significant, which is 1. Next, in order to obtain the 3 bit, so we have to reflect your 2 bit combination. So now first combination will get 1 0 as your 2-bit, and then 1 1, then 0 1, then 0 0. Then above axis all the third bits are zeros, most significant bits are 0. In the below axis all 4 bits are ones. Next, to obtain your 4-bit combination, reflect the 3-bit combination. Then here we start with 1 0 0, 1 0 1, 1 1 1, 1 1 0. So like this, so we would obtain here, and the below axis if I place here 1, so we would end above axis with the zeros. Then I obtain here the equivalent codes from 0 to 15 in your gray code. So this is about our session today. So tomorrow, so how to convert your binary to gray code and gray to binary code, how to obtain that. So we'll see that. Okay.